Okay, in this video, let's take a look at how to implement Edwards Faulhaber matrix formula in Wolfram language. So the basic idea is really simple. If you have 1, 2, 3, 4, 5, 6 to n, how do you add them up? And now you have everything raised to the power of p, right? So Bernoulli, Faulhaber's formula, use Bernoulli number, has created such nice formula so you can compute them directly. There's another way to compute the sum. It's actually mentioned in the modern periods solved by Edwards. He comes up with a very nice formula for this type problem using matrix, and we are going to implement that and explain the code a little bit here to show you how to use this formula to solve this type of problem. So if you scroll down Wikipedia a little bit more, the key idea here is, say you have n numbers from 1 to n, and you recorded sum as 8. The very well-known formula for cubics is that the cubic of each k from 1 to n and sum it up, it's exactly the sum of 1 to n take square. So this is a really very well-known formula, and you can see a lot of math people printed that on their t-shirt. So what's more is, if we raise the power to 5, 7, 9, 11, we can also express this sum as 8, even though 8 is indeed a function of n, but we do not need the terms to show up on the right hand side. It's all about the first order sum. Okay, and we have a generic formula for that, but it only shows that for these odd numbers. And Edwards has a very nice matrix formula that works for both odd and even numbers. You can find the derivation of exactly how the formula was given in this paper, A Quick Route to the Sums of Power by A.W.F. Edwards. So I'm just going to illustrate the result and how it's linked to the code here. The key component for this research is the following matrix pairs. So on the left hand side is the sum of all the powers. Dot dot dot. And this is a really infinity matrix, equal to 1/2 times 2, 1, 0, 0, 3, 4, 4, 1, 10, 5, and so on. And we have zeros here, and the times u square, u cube, u fourth, and u fifth, and this is -1. Okay, and u here is simply 2 times 8. Here. U equal to 2 times 8. Here A is m times m plus 1 over 2. Okay. And what's inside this matrix? We call this F matrix. And here is F inverse. So it's F, just the number I list here. And then what we need is the F inverse here. So in the F matrix, we have item F, I, J, which are I plus 1, 2 times I minus J plus 1. And this square is the binomial. Okay, so this is everything inside this matrix. And of course, the above computation can be written as K odd equal to 1/2 times F inverse and times U square, U cube, U fourth, dot, dot, dot. So this is the F matrix. And if we compute the F inverse, then some of the coefficient will look like this. So 1/2 minus 1/6 over third, 1/6 minus 1/3, 1/4 minus 10, or minus 3/10, 3/5, minus 1/2, 1/5. And this is the F inverse, and of course we have more terms, and everything that's not showing here is exactly 0. Same thing as the 0 here. Sort of lower triangle matrix. And in this way, you can express this everything in odd terms. And let's recall that here we only have these odd terms. So what about even powers? For even powers, we have kind of similar formula, but a slightly different way to generate the G matrix. So for even terms, let's do the same thing. Sigma n square, sigma n fourth, sigma n sixth, dot, dot, dot. It equals to 1/2 times 2n plus 1. The sum for all even numbers, you have to include the number of terms. And you have a G matrix, and take the inverse, and times very similar vector, but we start from U, U square, U cube, and the U fourth. So what is the G matrix? The G matrix looks like G equal to 3, 1, 5, 0, 5, 7, 1, 0, 1, 14, 9. And everything on the upper half is 0. Dot, dot, dot. And the G matrix is generated by Gij, that's the terms inside this matrix, and it looks like I plus 1 minus J plus 1 plus I 2I minus J plus 1. Here, both square brackets are binomial. Okay. And what's so interesting is there is a relation between F and G. So here, the G matrix can be computed directly through the F matrix. It is F plus 1 f. And here, filling with 0. So the first row and the first column are all zeros, except the item on the left upper corner. So in this case, we can just implement this nice formula for these power sum for both odd and even powers. Now let's compare the actual implementation with our notes. Both function or matrix that we use is called a sparse array. It's quite clear that we only need at most half of the matrix to be filled, and the rest of them, or the upper triangle, is simply zeros. So sparse matrix or sparse array function is our really good choice here. And let's take a look at the implementation of G. So G is sparse array, which is associated with F. F is mat1. You can see F is mat1. And the second part is using 1, 0, 0 mat2. This is a syntax sugar that matches exactly as this formula. So the first line is 1, 0. Second element, 0 mat2. The 0 corresponds to the 0 here. And you can see mat2 is precisely between these zeros and these zeros. So this array flatten will automatically fill the actual value in this region for us. And what is mat1 and mat2? So in the math expression, so F and F looks the same, but actually it really doesn't make sense if they are the same. This can be shown that by counting the number of rows. Of course, the rows in my notes are in just to illustrate the structure of the matrix. But if you want to run the sum, say from 2 to 10, only the even numbers. So there are only 5 numbers there. Therefore, the matrix here, F, you have to care about the number of terms that you need to use. The reason is 1 to 9 is the same number of 2 to 10. So for this number or this matrix to be filled in, you do have to get rid of some terms. And this is the exact implementation here. So the first F outside, say it comes with 5 rows by 5 columns. Then the guy inside it should be less than the dimension of that, precisely by 1. So that's why I put Fn-1 here. And this was the original formula, but you can see, knowing just writing down the formula is really not enough. And you have to be careful about actual number of terms that fits inside this type of matrix operation. Now let's do the actual computation. Here I've prepared some examples for you to study. First, let's load these 2 functions. Now Fm and Edwards Faulhaber matrix functions are all defined. So if we run this function on 8 elements, then we have 2 sparse array objects for F and G. And we can verify that these equations actually works for us. So assume m equal to 7. And just follow the Wikipedia. Let's first check all the sum by all the powers. So I is from 3 to 13. Jump by 2, step length 2. So we have 3, 5, 7, 9, and so on. And these are the polynomial of those sums in terms of n. Now let's replace that with the Edwards-Faulhaber matrix method. So recall that we have a matrix F times 1/2 and times a vector of u. So let's go back to our notes. This is precisely the formula we use for this type of multiplication. So it's 3, 5, 7, 9, all the powers, times 1/2 equals 1/2 times F inverse and 2, 3, 4, 5. So this is the actual implementation. And the m in -1 here is to control the actual number of rows that we needed. So you can compare the m-1 with the index here, and you can find a simple linear relationship between them. So that's how you adjust whether you should put m or m-1 here. And then we compare the v1 versus v2. v1, v2 is the same sum using two different ways to compute. And u here use precisely the 2 times the sum of 1 plus 2 plus 3 up to n. So these two sums matches. And let's take a look at the g-type. The g-type is for the even powers. Let's go back to our notes. We do have a formula for g, but we can skip that and use this formula directly. And f plus 1 and this is f minus 1. So for the power sum for each I from 2 to 14, and the step length is 2. So it only includes even power sum. And let's do that for this one again. So in this case, we have to include n, the number of terms, just like this part. And 1/2 times 2n plus 1 times g inverse and times a u vector. Here, we do that again. So you can see these two actually matches term by term perfectly. And indeed, we have a very nice identity between the two ways to compute the same form. In the last step, there is also a very nice identity to relate f and g. So it's by f inverse equals y times g inverse times x inverse. And x and y are defined below. Say we have fg is for 50 terms. So those are quite a large matrix. And if x inverse is a diagonal matrix, and each one on the diagonal is 1 over k plus 1. And y is also a very simple diagonal matrix. Let's take a look at it. Only the terms on the diagonal is defined. And what about y? Diagonal terms 3, 5, 7, 11, 13. So these are two really simple matrices. So their inverse are extremely easy to compare. So the formula says inverse, the matrix inverse of fg equal to y times inverse fg g times x inverse. Let's check. It is true. So do not really have to compute the large matrix inverse twice to compute that. So if you have an inverse of one item, the other can be computed really simply. That's everything for this video today. Before we finish, let's just take a quick look at how the cover was created. It's simply the large matrix and you take a screenshot of it. And that's it. Thanks for listening. See you next time.